We're moving away from a general antiderivative and we're going to find a specific antiderivative. Let's go ahead and do this work and then we'll talk about it. We're given that f prime of x is equal to the secant squared of x, and we're told that f of pi over 4 is equal to 5. We're asked to find f. As we said in a previous video, the derivative with respect to x of the tangent of x is equal to the secant squared of x. We are finding the antiderivative, so when we see secant squared, we're asking, hey, what function do I differentiate in order to get the secant squared? Since the answer is the tangent, we know that f of x is equal to the tangent of x, and don't forget our constant that shows up every time we antidifferentiate. But now we're told specific information here. We have that f of pi over 4 is equal to 5. This information is called an initial condition. Remember in a previous video, we said that if, we used an uppercase, f prime of x is equal to 2x, then f of x is equal to x squared plus c. And I talked about having a family of functions as an answer. If I'm given a point that's on the graph of one of the functions, then that identifies it as a specific function, and I'm able to identify what c is in particular. And so here we have the information that f of pi over 4 is equal to 5. So f of pi over 4 is equal to the tangent of pi over 4 plus c, and that is equal to 5. Since the tangent of pi over 4 is 1, we have 1 plus c is equal to 5, which means that c is equal to 4. Yay, we found c. That's not the answer to the question, right? We were asked to find f. And so f of x is equal to the tangent of x. We got that from antidifferentiating. And then the initial condition tells me that c is equal to 4. So f of x is equal to the tangent of x plus 4. All right, let's look at another one. Same instructions, find f, and here we have that f prime is equal to x plus 1 divided by the square root of x, and the initial condition is that f of 1 is equal to 5. We do not have a quotient rule for antidifferentiation. Therefore, our first step here is going to be to simplify. And first, that means we're going to give each term its own denominator. Right, each term in the numerator. So I have f prime of x is equal to x over the square root of x plus 1 over the square root of x. And that's going to be x to the, well, it's the square root of x plus 1 over the square root of x. I want to use the power rule. So I'm going to say that f prime of x is equal to x to the 1/2 plus x to the negative 1/2. If you can do all this in your head, great. Now I'm going to use the power rule, which means we're going to, for each term, add 1 to the exponent and divide by the new exponent. And I should say it's the power rule really in reverse. F of x is then, I usually start with the exponent. So for x to the 1/2, I'm going to write x to the 3/2, and then I don't even have to think about that I'm multiplying that by 2/3. Plus, you'd be amazed at how many calculus students forget how to add 1. If my exponent is negative 1/2, then when I add 1, I get 1/2. Dividing by 1/2 looks like multiplying by 2, plus our constant. This would be a fine form for an answer, but we do have the initial condition that f of 1 is equal to 5. F of 1, substituting 1 in place of x, is going to give me 2/3 plus 2 plus c, and we're told that that result is equal to 5. I believe that means that c is going to be 7/3. So f of x is equal to 2/3 x to the 3/2, totally fine, leave it like that, plus 2x to the 1/2 plus 7/3. Next, we're going to get into something that's a little more interesting. We're still going to find f. Now we have a second derivative. F double prime of x is equal to 20x cubed plus 12x squared plus 4. We have two initial conditions. F of 0 is equal to 8 and f of 1 is equal to 5. We'll see why we need both of them in just a minute, but first let's go ahead and do our anti-differentiating. F prime of x is going to be, for 20x cubed, I'm going to add 1 to the exponent. That's going to give me x to the 4th. and then divide 20 by the new exponent of 4, and I'm going to have 5. So that's 5x to the 4th. Next up, 12x squared, I'm going to add 1 to the exponent, so I get x cubed. Divide by the new exponent, which is 3, and so 12 divided by 3 is 4. I get 4x cubed plus 4x plus the constant. Sometimes if I have multiple initial conditions, they might give me information about a derivative, like f prime of 0 is equal to 8. If that were the case, I would use the information right now. But all the information that I have is about f. F of 0 equals 8, f of 1 is equal to 5. So let's go find f. I say let's go find like it's going to be out there somewhere. F of x is equal to 5x to the 4th is going to, the antiderivative of that is going to be x to the 5th. 4x cubed, you can verify the antiderivative there is going to be x to the 4th. And then the antiderivative of 4x is going to be 2x squared. Plus cx, we could go c1 and c2, it doesn't really matter. I'm going to say cx plus d here, because we're going to find what c and d are and then be done with it. Now, f of 0 is equal to 8. F of 0 is equal to, well, f of 0 is equal to 0x to the 0 to the 5th, 0 to the 4th, 0 squared, 0. It's d. And so I immediately know that d is equal to 8. Cool. F of 1 is equal to 5. So f of 1 is going to be 1 to the 5th plus 1 to the 4th plus 2 times 1 squared plus c times 1 plus d, but we know d to be 8. It equals 5. Oh, I forgot to point out. We have two constants of integration, or excuse me, I got ahead of myself. That's for the next module, or the next chapter. I have two constants that I got from anti-differentiating. That's why I need two initial conditions. It gives me, it's a system of equations essentially. Anyway, the arithmetic here is that c is equal to -7, I think. Yeah. So f of x is equal to x to the 5th plus x to the 4th plus 2x squared minus 7x, that doesn't look right, plus 8. And that's our function.